Hello Year 11. This is a video going through the latest mock exam. So that's the mock exam that you sat in 2017. And during this video I want to show you how to get full marks, show you a few tips, a few techniques to use when answering the questions. But most importantly, going to give a focus on language to make sure that the language that you will use in the exam will be the best language and the language that can get you some marks. This video will be relatively long, but the good news is that you can skip through those answers that you got correct, because clearly you understood how to get the marks on those questions. So you only need to view the questions where you miss off some marks. As we go through, if you write on your mock paper the correct answers and any additional notes that you want to make, then that will just be evidence that you've gone through this and you've looked through it with a focus and with the attention to try and get as much feedback as you can on this mock paper. So here we go, we're on question 1 and let's begin. So this question is about rates of reaction, so a topic that you won't have seen for quite some time. It was done back in year 10, towards the start of year 10, so a little chance to remember. But the rates topic is, the language in this topic is perhaps the most crucial of any of those topics, because it's so easy to miss off some marks, and we'll see that as we go through. So question 1 says, a student investigated the rate of reaction of magnesium and hydrochloric acid, and we've got there the equation. It says the student studied the effect of change in the concentration of the hydrochloric acid, and she measured the time for the magnesium to stop reacting. So we've got our 4 different flasks, we've got our different concentrations, and actually they've indicated in those pictures the 2 molar, or the 2 moles per decimeter cubed solution, which is the most concentrated. You can see it is reacting the fastest. We've got the most number of bubbles present in the picture. So question A says, the student changed the concentration of hydrochloric acid. Give 2 variables that the student should control. So she just wants to investigate the concentration. Everything else needs to be kept completely the same. So what else could affect the rate of reaction? Well, we're thinking about temperature. So the temperature should be the same. We've got the magnesium here is a solid, and you can see it's a long strip of solid. The mass of that magnesium must be the same, and also the surface area of the magnesium. Obviously, if we used a powdered magnesium, it's going to react a lot faster. So we've got to make sure that the type or the structure of that magnesium is the same. So I think I'm going to choose mass of magnesium as my other answer. What else could you have included? You could have included surface area, as I've mentioned. Surface area. I'm going to make sure, whenever I do this, of magnesium. I'm going to make sure I'm being extra clear what it is I'm referring to. And the hydrochloric acid, is there anything about that? Well, you can see that they've actually kept the same amount. You can see it on the diagram. What do we call that? We call that the same volume of HCl. Most importantly, right, language, volume or mass, we are not using the word amount. Okay, so amount is a kind of a banned word, right? We don't want that. Okay, amount doesn't get you any marks, it's too vague. It's something that you might have been able to say in key stage 3 in year 8 or 9, but now at GCSE that's just not going to get you anything, and you know better than that. So we're going to be as detailed as possible. Any of those will get us the mark. Part B, again, language is going to be really important for this question. It says the rate of reaction increased as the concentration of hydrochloric acid increased. And we've got 2 marks. We need to make 2 points about this. If we're ever explaining about rates of reaction, there are 2 phrases that we want to that we want to remember, that we want to get into our answer as much as possible. Reactions occur because of collisions, but let's add to that collision frequency, or the frequency of collisions. And remember, those collisions can be successful or unsuccessful. So let's just put in there successful collisions. You'll recall that when something collides, it's got to have enough power, or enough, I shouldn't say power, enough energy for the reaction to take place. And if there is not enough energy, or those particles don't have enough energy, they'll just bounce back off each other. So there are two sort of key phrases that we want to always remember when we come to a rates question. This one is asking us specifically about concentration. So first thought is, does concentration affect the success of collisions? In other words, does it affect the energy of those particles moving around? Well, in this case, not really. Those particles are still going to be moving at the same speeds. What it does do, though, is going to increase the frequency of the collisions. So we're going to get 1 mark for making that point, and we're going to get our second mark for saying, well, why is it increasing the frequency of collisions? So how does concentration affect it? So particles, the number of particles in a specific space, you've got to qualify it with a specific space. So let's say I'm going to choose 1 centimetre cubed. You could just say per volume, or per unit volume. So number of particles in 1 centimetre cubed, that could be anything, increases. What does that lead to? It leads to an increase in the frequency of collisions. So I've got in there my frequency. If you don't qualify that by some sense of time, if you just said that there are more collisions, that does not get you the mark. And the reason is because if we left it for a very long period of time, those reacting particles are still going to collide the same amount in total. We're still going to get the same amount of a reaction happening, but it's the speed. Okay, so it's how quickly are those collisions taking place. And we've also got to qualify the volume. So it's not just more particles, it's more particles in the same space. Okay, so that's how we get our 2 marks there. Notice I'm doing bullet points. Bullet points are always, absolutely fine. You can use them as much as you like in chemistry. In fact, it's quite a nice way of organising your answer, so happy to do that. Part 2, explain why increasing the temperature this time. Right, let's think about those 2 key parts again. Can you remember what they were? So we're looking at collision frequency, and we were looking at the success. I want to make that successful collisions. So if I increase temperature, is it going to increase the frequency of collisions? Well, increasing temperature, the particle is going to move around a lot faster. They've got more energy. So yeah, they're going to bump into each other more often. Is it going to increase the success of the collisions? Yes. They're bumping into each other with more energy. It's going to increase the rate of reaction, or the rate of successful collisions. So this time 3 marks. So first, what effect does temperature have on the particles? So increase in temperature increases the speed the particles are moving, or increases their energy. Increases the frequency of collisions, and more collisions will be successful as particles collide with more energy. 3 marks. Again, I've got in there my qualification of frequency. I've not just said increase in collisions. And I've also gone on to say about how collisions will be more successful. I'm just going to go and change my pen. Right, got my new pen. You're going to see it a bit better now. And we're on to question C. So a little bit about titrations. So into something from year 11 here. Let's have a look at the question. So it says, the student had a solution of sodium hydroxide with a concentration of 0.1 moles per decimeter cubed. She wanted to check the concentration of a solution of hydrochloric acid. To find the concentration, you're going to do a titration. She used a pipette to transfer 5 centimeters cubed of hydrochloric acid to a conical flask. She filled a burette with 0.1 moles decimeter cubed of sodium hydroxide solution. So it's already given me part of that method. She started off doing the titration. All we've got to do is describe how she should use the titration to obtain accurate results. What's the next step she's going to do? So she's got in there her hydrochloric acid in the conical flask, and she's filled up her burette already. She at the moment hasn't mentioned indicator. So what does she need to do? She needs to add an indicator. Just remember, does that indicator go in the conical flask or in the burette? Well, let's just remind ourselves. Here's the conical flask. Here's my pretty dreadful drawing of a burette. Drip, drip, drip. It needs to go into the conical flask, doesn't it? That's where the reaction is taking place. That's where the mix is happening. So add an indicator to the conical flask. Right, she's got all of her ingredients. What does she need to do now? She needs to slowly add, what was it? It was a sodium hydroxide. Sodium hydroxide, I'm going to put NaOH for short, from the burette. Oh no, this pen's going as well. I'm going to have to get another one. Hang on. Right, third pen. I've been to Miss Woodhouse relying on him for a decent pen. Here we go. So slowly add NaOH from the burette, and let's see, what else do we need to put in there? From the burette. Oh, I should put in there to the conical flask. There you are, that's what I was thinking of writing earlier. To the conical flask. When do I stop doing that? I need to stop when there is a permanent colour change. Right, that sounds pretty good to me. It's 4 marks. Where am I going to get those other marks from? Well, do you remember when you're doing the titration, you had to repeat the titration, and once you'd repeated it, what do you do? You then took an average. So that's always why we repeat. So we repeat and then average the titration results. Right, 1, 2, 3, 4, 5. I've actually got 5 points in there. And quick little check of the mark scheme. Those two are actually 1 point, but kind of makes sense to put them in as 2 bullet points. So all of that for your 4 marks. When I was marking this, it seemed that lots of people went into great detail about how the titration was set up, what we did, but half of that's already been described to us. So just make sure we read all of the information in the question and then think, what is it really that question is getting at? It doesn't want us just to repeat what's there. It wants us to carry that story on to think, right, well, what happens next? So that is question C. Let's final question of part of question A. So sodium hydroxide neutralizes hydrochloric acid as shown below. So we've got NaOH plus HCl changes to NaCl and H2O. And we've got some figures. So the student found that 27.2 centimeters cubed of 0.1 moles per decimeter cubed sodium hydroxide. Right, let's just double check which one's the sodium hydroxide in our equation. Well, we obviously need a bit of sodium there, and hydroxide, remember that is O and H. So these two figures refer to this. Neutralizes 5 centimeters cubed of hydrochloric acid. So hydrochloric acid is HCl, so the 5 there refers to the HCl. It says calculate the concentration of the HCl in moles per decimeter cubed. Give your answer 3 significant figures. Okay, so 3 significant figures, very important. That's going to get me a mark, and it would be a silly mark to lose. What I might just do before I forget, if I come down to the answer here, here's the space for the answer. If I just write in there underneath, whilst I remember, 3 sig figs, when I come to put my answer in, that will just be a little clue to put that in the answer, to make my answer 3 significant figures. Right, back to the question. So, I want to find the concentration of hydrochloric acid, but I've got the information, I've got more information about NaOH. So what I'm going to do is I'm going to use that information to work out the number of moles of NaOH. If I've got the moles of NaOH, I can work out the moles of HCl. And if I've got the moles of HCl, I can work out the concentration of the HCl. Sounds complicated. What you might have done in class is some of these little tables. So what I need to know is, what I've got is the volume and the concentration and moles. They're the 3 things I'm interested in. NaOH, I've got the volume, so that's 27.2. Concentration is 0.1 moles. I'm going to find that out in a moment. HCl, the volume is 5. I've got to remember one of the equations. So moles equals volume times by concentration. The most important thing in this, though, is that the volume has to be in decimeters cubed. In the question, the volume is given as centimeters cubed. So I need to change those centimeters into decimeters cubed, which I do by dividing by 1,000. So let's go through that. I'm going to work out the moles of NaOH first. So that equals moles of NaOH first. So that equals 27.2 divided by 1,000 times by 0.1. Just taking the information from here. Remember, you need to make it in the decimeters cubed divided by 1,000. So that equals, oh, I've left my calculator. Give me a second. Right, I'm back. So 27.2 divided by 1,000 times by 0.1 equals 2.72 times 10 to the negative 3. Remember, that's in standard form at the moment, so if I didn't want it in standard form, it would be 0.0272. Right, so that's my moles of NaOH. So I've got that. I can put that into my table if I want to carry on using this. My moles of NaOH are going to equal the moles of HCl, because in the equation, 1 of NaOH reacts with 1 HCl. That is our ratio. So our ratio of 1 to 1. Ratio 1 to 1. So moles of HCl are going to be exactly the same. 2.72 times 10 to the negative 3. Right, finally I need to work out the concentration. So if I've got moles equals volume times concentration, what does the concentration equal? Well, concentration is moles divided by volume. If I just put that up here, I'm going to put C for concentration equals my moles divided by the volume. Okay, so my moles is 2.72. So my concentration of HCl equals 2.72 times 10 to the negative 3 divided by 5. Can you spot what I need to do with the 5? Yeah, I need to divide it by 1,000 to make it into decimeters cubed. So 2.72 times 10 to the negative 3 divided by 5 divided by 1,000. Right, so divided by 5 divided by 1,000, 0.544. Is that 3 sig figs? There's my reminder. Yep, in this case, nice and straightforward. Don't need to change it. And that's question 1. So moving on to question 2, and this one was quite a tricky question, all about energetics. Again, a year 10 topic that's very specific. So something that you might not have covered in your revision, or certainly we haven't necessarily gone over it in class, but something that definitely needs a bit of focus before we get around to that exam. So the first question is asking us about an exothermic reaction. It gives us the details, and the question says, explain in terms of bond breaking and bond making. So I'm going to have to mention those in the answer. I've got to say those 2 phrases. Why the decomposition of hydrogen peroxide is exothermic. So exothermic means it's giving out energy. So the way I can go about answering this is that I can say that energy released from making bonds. So there's my bond making. Now, if it's exothermic, that energy release has got to be really high, doesn't it? It's got to be higher, in fact, than the energy taken in by breaking the bonds. So energy released from making bonds is greater than the energy, I could say, required or needed to break bonds. I always think of it as if you want to break something, I don't know, like let's say best way to break something is using a sledgehammer. Let's go big. Let's go for a sledgehammer. If you're going to break something using a sledgehammer, you're going to need to put in a lot of energy. It is tiring work heaving that sledgehammer around. So you're using loads of energy to do that breaking. Making bonds is the opposite. All right, it's really easy to make bonds. Because it's exothermic, the making, the releasing of the energy is going to be greater. Okay, let's go on to part B, and it's given us an energy level diagram. Okay, so hopefully this is familiar to you, but we've got a few letters which we're going to be asked about to know. We've got to know what each of these different letters refers to. So let's see what the questions say, and then we'll come back to that diagram. So it says the energy changes A, B, and C are shown on the diagram. Use the diagram to help answer the questions. How do you know that this reaction is exothermic? So again, exothermic, we're talking about energy being given out. That's a very simple explanation. Energy being given out. If we look at the energy diagram, you've got our H2O2 here, and our products on the right hand side. Well, the energy there has gone down. Okay, so why is energy being given out? So it says here energy on the left, but what we could really say, I could add an extra word in there, which is important in our understanding, is that that's the chemical energy. So how much energy is kind of wrapped up in that H2O2 and in those products. So in the products, we've got less chemical energy than we started with. So where's that extra energy gone? Think back to your physics, of course, energy's got to go somewhere. It can't just disappear. Energy can't be created or destroyed. It's got to change from one thing into something else. So in A, the energy change, that energy is being released as heat. So how do you know that the reaction is exothermic? The chemical energy of the products is less than the reactants. It's only one mark, so I don't really need to go into any more detail on that. That's a pretty straightforward answer looking at that energy diagram. So that's kind of A looked at. Part 2 is going to ask me about B on the diagram. So it says the decomposition of hydrogen peroxide is slow. What does this suggest about energy change B? Well, here's B. We've got a bit of a barrier here where our chemical energy needs to go up before then coming back down to be our products. So B refers to activation energy. I'm just going to put AE for activation energy. So if it's slow, that suggests we've got a big barrier. It's going to be really difficult for the hydrogen peroxide to break down into our products. So activation energy B is very large. It forms a big barrier. Activation energy is very large. Oh, hang on, let me just check my writing. What does this suggest about energy change B? Activation energy, I might just, I haven't rephrased that very well, have I? Because I haven't actually mentioned B. I should say, just to clarify that, B is activation energy. Just to make sure I've mentioned what B, then I've got B into my answer. Part 3, hydrogen peroxide decomposes quickly when a small amount of manganese oxide is added. Right, well, what the heck is manganese oxide doing? Why has that suddenly appeared? Well, it's sped up the decomposition. So it's sped up the change. Manganese oxide is acting as a catalyst. What does a catalyst do? It's going to have to be something to do with this diagram and energetics, otherwise why am I being asked about it? So if you remember that a catalyst reduces the activation energy, so it becomes easier for the reaction to take place. So I'm going to get in there, explain why manganese oxide is a catalyst. A catalyst reduces activation energy. So this barrier B becomes smaller. So more of those collisions, well, it's not actually collisions in this case, more of the hydrogen peroxide has the energy to decompose. Perfect, right. Let's go on to C. We've got another little diagram. Looks like we're going to be asked about a practical. So a student did an experiment to find the amount of energy produced when hydrogen peroxide solution is decomposed. Here's the apparatus. And we've got thermometer beaker, hydrogen peroxide, manganese oxide. So we're obviously looking at the temperature. The student first measured the temperature of the hydrogen peroxide. Then the student added the manganese oxide. What was that doing there? Remember, that is a catalyst from our last question and recorded the highest temperature it reached. the temperature rise was smaller than expected. So why did the temperature not get up really high? We've just got this big reaction taking place. Smaller than expected. So somewhere or something is causing the temperature to be a bit smaller. And the reason is because as the reaction takes place, as the temperature is increasing, straight away it's beginning to lose heat. It's beginning to lose that energy as it goes off to the surroundings. Some of it's going to be heating up the beaker itself, some of it's going to be heating up the air. So what we could go in for here is during reaction, energy, or I'm just going to change that to heat energy, is lost to the surroundings. So we're never going to get up quite to that highest temperature that we could do. Why was there a lot of energy loss? Well, it could be that we didn't have a lid on there. Remember, that's a way of improving it. I'm going to add that in, no lid. Or, because that's not really saying why it's smaller than expected, because even with a lid, you still get that heat lost. Why else might it be smaller? Could be that our hydrogen peroxide we started off with was slightly lower concentration. H2O2 was lower concentration than predicted. Any of those three get us a mark, so we can get our 2 marks for that answer. And that's question 2. And the final question in the paper was about organic chemistry. So this again is going back to some year 10 work. So something that needed to be revised, needed to be refreshed, because we're going back some distance. Let's have a look. So the first question, it says, to make a plastic such as polyethylene from crude oil involves many processes. So we've got our crude oil to start with, we're going to distill it. That could be quite useful. Going to then crack it. So we get our molecules of alkene, and then we're going to heat it for polymerization, and we get our large molecule. And you can see that each of those little alkene molecules is joined together in a long chain. So lots of information in that scheme. Describe how crude oil is separated into fractions. Well, if I'm not quite sure where to start, if I look back to my scheme, I've got crude oil changing into a fraction. And it says there, heat for distillation. So it obviously involves distillation. That might prompt us to think of fractional distillation. So I'm going to add that in as my first point, fractional distillation, as a key phrase. How does fractional distillation work? It also tells me heat, so heat must be involved. So the first thing that happens is all of the crude oil is vaporized or turned into a gas. So heat the crude oil to vaporize it into a gas. The key word here, vaporize, gets us a mark. What happens once it's a gas? So you might remember, do you remember the fractionating column? So if I draw a really pretty rubbish fractionating column, here it is, and it had all those different levels. And the gas comes in, and it's going to rise, because gases always rise, don't they, when they're hot. So hot gases are going to go up. As it goes up, it's cooling, it's getting away from that furnace, is my pretty rubbish. That doesn't even look like a flame, does it? That's supposed to be a flame down there. Here's my flame. So we're getting further and further away from that flame. It's going to cool down. And as those gases cool down, they're going to condense back down into a liquid. So gases condense into a liquid, and they're going to separate. They separate according to their boiling point. Okay, so what is the key phrase or key word in this? Well, the fact is that they've got their boiling, they condense, and they're condensing according to their boiling point. They separate according to their boiling point. 2 marks. Right. Last page. On to the last page, home straight. Oh, I'll tell a lie, there's one more. Forgot about that one. Right, here we go. Let's get through this then. So B, part 1. Ethene is produced by cracking the hydrocarbons in the naphtha fraction. Balance a simple equation for this reaction. So everything on the left has got to end up on the right. We've got 10 carbons to start with. We've used up 4, 6. So there's another 4 left over. Okay, so I'll just add that up here. I've got 4 carbons left over. Let's just check what's going on with the hydrogens. 22 to start with. Used up 10. Used up 4, so I've used up 14. So I've got 8 hydrogens left. So 4 carbons, 8 hydrogens left. I can't make another butane, can I? I haven't got enough. But I can make 2 more of those. So in total, that takes it up to 3. So 3 ethene plus the butane makes the decane. Describe how cracking is carried out. So what do we need to do to crack something? You may remember this from doing it back in year 10. Just trying to think. Now I'm going to have to do another drawing here. You had your little, do you remember having the mineral wool and some little pieces of porcelain, and you heat up, here's my pretty rubbish Bunsen burner, you heat up the porcelain and the oils that are in the mineral wool, pass over that, they vaporize, and they pass over the catalyst. When they do that, that's when they kind of split apart, that's when they crack, and you're going to collect up those different smaller pieces. So what's the key to that? Well, we've used heat again, haven't we? So we have used a heat to vaporize the fraction. And then we've also passed it over a catalyst. So pass the fraction over a catalyst. Should we just name what that catalyst is as well, just to make sure we've covered everything? And that catalyst was, what did we use? We used a porcelain. I think that's how you spell porcelain. Porcelain pot. Or it was a ceramic. We could just say ceramic, probably that would be fine. So a ceramic. Okay. Cool. 2 marks. Part C. Alkanes such as butane do not form polymers. Alkenes such as ethene do form polymers. Explain these statements. Right, so just got to remember, what is the difference between an alkane and an alkene? We've got given the formula. If I just draw those, so here's our alkane, 1, 2, 3, 4, and then I'm going to put my hydrogens in there, H, 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 H. Right, we've got 10 hydrogens, 4 carbons. Alkenes, right, we've got ethene. What was the difference? We've got carbon, carbon. We've only got 4 hydrogens to play with. So 1, 2, 3, 4. Carbon needs 4 bonds. the other one was a double. So you might remember that an alkene has a double bond. So why is it that we can attach these alkene molecules together, but we can't attach alkanes? So the reason is because of that double bond. That's the only difference. It has got to be something to do with that. So my first point, if I can't even remember why, let's just get that difference in. So alkenes contain a double bond. Alkanes do not. Got to make the comparison. What happens to that double bond? Well, double bond can break, and ethene can attach to another ethene. So we can begin to attach those together. There's a little model that you might have used where students kind of cross their arms to represent the double bond. If you break that double bond and pull your arms apart, you can then hold hands or hold on to the person next to you. So if you imagine you're like the alkene with a double bond, if you break that double bond, so if you stop crossing your arms, if you break that double bond, you're then able to hold on to other things. And that's effectively what's going on with the alkene. That gets us the 2 marks. Right, last question. We are truly on the last one now. So ethene molecules form the polymer polyethene. One molecule of polyethene will contain thousands of carbon atoms. And here is what a little section, what a part of it will look like. So where the bond is at the side, that's just going to carry on in the same manner. Propene molecules form the polymer polypropene. So now we've got propene because we've got 1, 2, 3 carbons. Draw a diagram to represent a part of a polypropene molecule. So remember that double bond is going to break and it's going to form new bonds on either side. So if I'm going to draw exactly the same, I'm not going to alter at all, except for I'm not going to put a double bond in. So the carbon can now attach to another one on the side. And that carbon is going to do exactly the same. So that's not got a double bond, it's going to attach to another one. And this is going to go on and on and on. But for your souls and mine, I'm going to only do 6 carbons because that's what's in the diagram at the top. I've got to get my mark, I've got to make sure my CH3 groups are there every time. I've got to make sure that my bonds at the sides are sticking out because remember it's still going to attach on to another ethene. And I want to make sure I've got single bonds throughout. So that brings us to the end. Hopefully that was helpful, a helpful way of doing this. Saves us going through it in a class and allows you to go through in your own time. If you've still got some questions, maybe there was a particular question that you weren't quite sure about, or you'd like to be explained in a bit more detail, very happy to do that. So me or Mr. Woodhouse will happily go through it in a bit more detail with you. Just come and find us at a suitable time. In class is not a suitable time because we're going to be doing lots of awesome chemistry in class. So if you do want to take up the opportunity, you're going to have to find us before school or after school or in a break time or lunchtime. But as I say, very happy to give you the time to do that. Awesome. All right. See you next lesson.